In continuation with centroid of line segment and centroid of plane figure, we'll try to see a few topics about centroid of volume, which is the geometric center of the body. We note here that this centroid of volume represented by GV, center of mass represented by GM, and center of gravity represented by G subscript W, all of them mean the same thing when the density is constant in every region of the body. Otherwise they are not identical, and we note that center of mass and center of gravity will be equal, but in general center of volume or centroid and center of mass, they are different. Now we'll try to see how to find the centroid of volume with a couple of examples. In specific, we'll see how to locate the centroid of a parallelepiped, a pyramid, a cone, and a hemisphere, which we call primitives. And then we'll try to go into the topics of locating the centroid of composite objects, and also touch upon center of mass and center of gravity. First, let us present the formulae for x, y, and z coordinates of the centroid of a volume, and then try to touch upon these primitives. The x, y, and z coordinates of centroid of volume are given by the three equations here. Notice that these three equations are again very familiar to us. In place of the elemental area, you have an elemental volume in both numerator and denominator in all the three formulae. Once we identify this, the task for us is to suitably identify the elemental volume and perform the integral over the entire volume of the body. That is what the subscript V at all the places indicates. To begin with, we'll start with the first primitive, which is a rectangular parallelepiped, which is a box kind of thing with all right angles. We have a big rectangle here, a rectangle here, a rectangle here. That is the reason why we call it a rectangular parallelepiped. The first thing we do is set up x, y, z axis as shown here, and consider an elemental volume shown by PQRS with a thickness of delta x. The elemental volume is shown here for clarity. A PQRS is one face, and you have another face at a distance of dx. We can very clearly see that PQ is equal to length b, that is what we have shown here, and PS, distance from here to here, is distance from here to here, which is h, that we have shown here. And thus we can write the elemental volume as, we substitute the value of dV as taken from here into the formulae, that is x times bh times dx. Similarly, bh times dx, the constant term bh gets cancelled down. In the numerator we have x times dx, integral of which is x square over 2. In the denominator you have integral of dx, the integral of that will be x. If you evaluate, you will see that x coordinate of the centroid is at a distance of L over 2. In a similar fashion, we can show that the y coordinate is h over 2 and z coordinate is b over 2. That is for a rectangular parallelepiped. The centroid will be located by setting off distances halfway across length, height, and breadth. In passing, we may note that the volume of this rectangular parallelepiped is given by LBH. Thus, we would locate the centroid of the rectangular parallelepiped by traveling halfway across this L by 2 distance, and then halfway vertically, and then halfway along the z-axis. We will locate the centroid by G. Okay. We will try to see the other primitives, that is, we'll try to touch upon how to find the centroid of a pyramid, of a hemisphere, and of a cone. The next primitive we consider is a square pyramid, shown here. We call it square pyramid because the base formed by these 4 points is a square. This pyramid has a height h, that is the perpendicular distance from the apex here to the base is h. The side of the base square, which is a, given over here. So this object is called a square pyramid. To locate the centroid of this square pyramid, we'll try to consider one thin slice as shown here, with hatched sides as shown here. We'll consider a thin slice, that is this is elemental volume dV. So we'll write an expression for this dV and then substitute it into the integral. To do that, let us note that the z coordinate varies from z is equal to 0 all the way up to z is equal to h. And if we take a section, horizontal section, such section will always be a square because the base is a square. If you take any cross section across a plane parallel to the base, it will be a square. And when z is equal to 0, the side of the square is a, and when z is equal to h, the side of the square is 0. If we denote the square side at a cross section with a height of z, we will see that when z is equal to 0, that side p will be equal to a, because when z is equal to 0, we are at the bottom face of the square, and this side is a. When we come to the height of z is equal to h, you won't have any square, it's a point, so the side is 0. Noting this, we can find a relation between the z coordinate of the slice we are considering and its side as. Thus, if we assume that the side of the slice varies linearly with the z coordinate, that is assuming this relation p is alpha z plus b, substitute z is equal to 0, p is equal to a, z is equal to h, p is equal to 0 into this equation. You will have two equations and two unknowns, alpha and beta. You can solve them to be beta is equal to a and alpha is equal to minus a over h. Thus we can write p as, if you substitute and simplify, you'll get the value of p as a multiplied by 1 minus z over h. Thus the area of this square that we obtain as one side is equal to p square, and we obtain the elemental volume dV as p square multiplied by dz. We note this and substitute into the formula to evaluate the z coordinate of the centroid of this pyramid. The elemental volume may be written as p square, that is the area of the size area of one top square multiplied by the thickness dz. We have already expressed the side p as a function of z in the equation. So with this we write elemental volume dV is equal to a square multiplied by the quantity in parenthesis multiplied by dz. Thus we write an equation for z coordinate of the centroid as, in the numerator we have integral z dV, and in the denominator you have integral dV. We will try to substitute the value of dV into these and try to simplify. Then substitute the value of dV as obtained from here and evaluate the integrals as shown over here. A square integral between 0 to h z multiplied by 1 over z minus h z by h whole square dz, and in the denominator you have dy. We'll try to simplify these by noting that this 1 minus z over h whole square is 1 plus z square over h square minus 2z over h. That will simplify to the indefinite integral shown here between the limits h and 0. Again, carefully note that the limits of the integration need to be from z is equal to 0 as given here, z is equal to 0, that is the base, to the apex. Apex is given by z is equal to h. So if we evaluate this integral, we will get the z coordinate of the centroid as we have centroid is obtained as 1/4 the height h. So we can locate the centroid on the figure as a point where the height is 1/4 on the axis. So we locate it somewhere here, and we say that the height of this point from z is equal to 0 from here to here we say is h over 4. We will try to do a similar exercise for the case of a hemisphere, a cone, and then try to look into composite objects which are made out of Boolean operations of these objects. In passing, we see that this quantity in the denominator, integral 0 to h of dv, is the volume of the pyramid. So if we evaluate the integral in the denominator, we get the volume of the pyramid as, thus the volume of the square pyramid is evaluated as this expression over here, which simplifies to 1 over 3 a square h, where h is the height of the square pyramid. We'll try to see as two more examples. One is a cone and another is a hemisphere. The hemisphere we consider is shown here with a radius of r, that is for any point on the periphery of this hemisphere. Its distance from the center shown here is r, as well as for any point shown on this base, the distance from center is shown by r. That is, we say we are considering a hemisphere of radius r. If we cut this hemisphere with a plane shown here, which is parallel to the base of the hemisphere, this circle formed at the base is what formed here is what we call base of the hemisphere. If we cut this hemisphere with a plane parallel to the base, we get a circular cross section whose radius we are denoting by a quantity a. We can very clearly see that if we cut a section very close to the base, the radius will be very close to r. If we cut a section very close to this point, the radius a of the circle obtained in the cross section will be equal to 0. This is very similar to what we have seen in the case of a pyramid. We will try to do the same thing here. I'll very quickly walk through this example, and I would encourage you to write each equation in detail and solve it on your own. We'll see that the area of the thin slice shown here is equal to pi into a square, where a square is given here. A is the radius of this circle as indicated by the dimension here, and thus elemental volume dV is area of the slice multiplied by dx. Dx is the thickness of the slice. Thus we write the formula for integral, formula for the centroid as integral x dv over integral dv. Note carefully that the limits of integration are 0 to r. If you try to simplify, you will get this x bar as 3/8 of the radius. So we locate the centroid somewhere here, where the distance between this point and this point, this distance is equal to 3/8 the radius. So we say centroid of a hemisphere lies at a distance of 3/8 r, where r is the radius of the base circle. We see that when the density is constant, the centroid of the volume, center of mass, and the center of gravity are all identical. We'll see one last example real quick in less than a minute and wind up this lesson. Similar to what we have done in the case of the square pyramid, we notice that the quantity in the denominator here indicates the volume of the hemisphere. Thus we perform the integral to realize the known fact volume of the hemisphere is 2/3 pi r cube. As a last example, we'll try to evaluate the x-coordinate, evaluate the location of centroid of a right circular cone. We'll do that in perhaps less than a minute. The cone we consider is shown here with a base which is a circle of radius r and a height h. Again, we note that if we cut this cone with a cutting plane which is parallel to the base, the cross section which you see in red here is a circle. Thus we show the elemental volume as, the elemental volume has a thickness of dz as shown over here. This height is dz, and it has a radius of lowercase r, which is given by capital R into 1 minus z by h, where capital R is the radius of the base. Note that this formula is very similar to what we have seen in earlier cases. Now we'll try to write elemental volume as pi r square multiplied by dz. Pi r square is the area of the circle shown over here, and dz is the thickness of the slice. Pi r square dz is the volume, which we write it as this whole expression shown here, shown in this, because we already know that r is this value given here. Essentially we are trying to express r in terms of z, because dz is the integrating variable. We will substitute in the integral and evaluate it between the limits 0 to h. At this point we have z is equal to 0. At this point we have z is equal to h. So we evaluate it between the limits 0 to h and try to and evaluate the z coordinate of the centroid of the right circular cone as h over 4. That is, we show it over here. This distance is vertical distance from base above is 1 over 4h. In passing, we note that the integral again in the denominator as shown here gives the volume of the right circular cone. The volume of the right circular cone is evaluated as V is 1 over 3 pi r square h, which is a known result for us. So far we have seen the topic of centroid, that is centroid of line segments, centroid of plane areas, and centroid of volumes. The next topic we'll see, the next topic that we need to see is how we locate the centroid of composite objects, that is an object which is formed out of, let us say, hemisphere and a cylinder, or a rectangular parallelepiped and a square pyramid. These topics we will see in subsequent classes.